Good morning, everyone. So since this is already 10 plus 10, so let's get started. So just an announcement on assignment 3. So assignment 3 has been released and it is due on April the 12th. And you have, oh, seems that we have a question here. Question do we have? Oh, yeah, sorry. Yeah, I'll update the course website. Yeah. Accordingly, I forgot to post the link on the course website, but it has been, I have updated the starter code and also the link to the handout in the GitHub repository. And it is due on April the 12th. And you have you have 3 full weeks to handle the assignment. Okay, and as we have mentioned, so assignment 3 is on loop invariant code motion and register allocator. We have discussed about register allocator in our previous tutorial. And in this tutorial, we'll be discussing about loop invariant code motion from assignment 2. Okay. Yeah, I will update thanks for bringing this up, and I will update the assignment handout after the tutorial. Any other questions? Okay, so if there are no questions, let us first, so in our previous tutorial, we have discussed about the programming portion of assignment 2. And in today's tutorial, we'll be continuing our discussion on assignment 2. And more specifically is theoretical questions. So let us first go through the question on lazy code motion first. Okay, so what I drew here is the control flow graph for the lazy code motion questions that you got. Okay, so let us first take a look at this control flow graph. Okay, our first question is therefore is, so why there's optimization opportunity for us in terms of lazy code motion? So specifically, where is the partial redundancy here? Well, we can clearly see that the partial redundancy is here along this path. Along this program path, right? The reason is because, so clearly we can see that the expression B plus C is evaluated twice along this program path. However, because it is not evaluated along the other program paths, hence this is not a full redundancy or global redundancy. This is only a partial redundancy, which is what a lazy code motion is targeting, right? Which, as we have discussed, is to optimize for partial redundancy with minimal register usage. Okay, so how are we going to handle for the lazy code motion in this case? Well, let us start by breaking the critical edges here. So as we can clearly see, so there are 2 critical edges here. So one is here, and the other is here. Because from the definition, we know that so a critical edge is an edge whose source has multiple successors and destination has multiple predecessors here, right? So we start by breaking the critical edges by inserting the synthetic blocks here and here. So our next step will, sorry, before we move on, any questions so far? No question. Okay. So our next step will therefore be compute the anticipated expression here. So let us consider. So for simplicity, we will not be dealing with expression b plus 1 here, because apparently this one is not partially redundant. We're only considering b plus c here. So consider expression b plus c. So in what region is expression b plus c anticipated? Well, let us consider starting from the point here. So remember that anticipated expression is a backward analysis. Therefore, the expression b plus c is started to be anticipated starting from this program point onwards. So let me erase the arrow here. The expression b plus c is anticipated starting from this program point onwards here. So what about the other program passes? Well, expression b plus c is anticipated from here to here until it reaches this program point, which involves a meet operator. So what about the expression b plus c here? Well, expression b plus c is anticipated here until it reaches to this point where the operand b has been killed. So where the expression where b plus c is killed here, because the operand, we assign a value to the operand b here. And because expression b plus c is no longer anticipated starting from this program point onwards, so therefore expression b plus c is not anticipated here, and therefore not here as well. We therefore conclude that the anticipated expression, the anticipated region for b plus c is here and here. Any question? So what about the will be available expression analysis? Well, okay, so before we go into that, so let us first consider the anticipation frontier for the expression b plus c. So recall that, so we said that, so the anticipation frontier is the place where the anticipated expression transits from 1 to 0 here. So therefore, there are two anticipation frontiers in this case. One is here, and the other is here. Expression for b plus c. So does this satisfy our condition for earliest placement? Because as we have discussed, the reason why we want to introduce will be available expressions is to filter out the anticipation frontiers where the expression is still available. So the question, therefore, we want to ask is, so now that we want to insert expression b plus c at this point, is the expression available at this point here? Well, the answer is no, right? So therefore, those 2 points are the earliest placement for the expression b plus c. So there are the anticipation frontier, and at the same time, also the earliest placement. Now the question therefore becomes, so can we postpone the expression b plus c? Well, the answer is no in both cases. The reason is because consider what we have on the left-hand side, right? So there is a use for the expression b plus c here at this program point. So therefore, we can no longer postpone the expression, the earliest placement beyond this point, because there's a use for expression b plus c here. And because of this, the basic block, so as we said, so the region starting from here, this point onwards, denies the postponement. Because of this, at this program point, when we try to postpone the earliest placement B plus C to its successors, this postponement will fail as well. The reason is because the successor here does not accept the postponement because there is a use for the expression B plus C here. Hence, they are also the latest placement. And by inserting the expression B plus C at its latest placement, we can clearly see that we make this B plus C, we make B plus C, which was previously partially redundant, globally redundant. And therefore, we can simply eliminate the redundant computation here. And hence, the program performance is more optimized compared with the baseline, what we had previously. Any question here? And in terms of the programming, it's similar idea to what we have discussed previously in the previous tutorial for the liveness analysis. Where let's say if we have an expression B plus C, let's take the anticipated expression as an example, right? Suppose that we have the expression B plus C, where the operand B comes from a final, let's say B is equals to phi B1 and B2. And B1, let's say, comes from this basic block here, and B2 comes from another basic block here. So what we will be doing in this case is that a possible implementation of this is that we set the expression B1 plus C as anticipated starting from this program point onwards, and B2 plus C as anticipated starting from this program point onwards. So this can be done by overriding the get boundary value method. Okay, but again, so this is just one possible implementation. Of course, there are other equivalent ways of doing it. Any question here? No questions? Okay, so if there are no questions, then let us continue our discussion for the loop invariant code motion. Yeah, sorry, just another comment. So as you probably noticed, so the question that the question that we are approaching here is pretty similar to the minimal example that we had previously in the tutorial, right? It's just in this case, the right branch has been made more complicated, slightly more complicated. But in essence, they are the same, right? So if you are still confused with this question on lazy code motion, perhaps revisit the minimal examples that we had in the tutorial. on lazy code motion, on how to eliminate partial redundancy. Well, I'm not sure exactly what you mean by time consuming. To be honest, I mean, I don't think so. I mean, but of course, it's not for me to comment on the difficulty of the assignment, right? Any other questions before we move on? All right, so if there are no questions, so let us continue our discussion on the second theoretical question, which is also part of your next programming assignment in A3, okay, which is loop invariant code motion. And you'll be getting a very similar benchmark in A3 for your loop invariant code motion analysis. Okay, so make sure that if you have any questions, please ask now. So let us consider the benchmarks that we have. Okay, so let us start by eliminating the instructions that are not loop invariant. Okay, so clearly z is equals to z plus 1 is not loop invariant here, right? So we eliminate this instruction. And similarly, a is equals to a minus 1, and a is equals to a plus 2, and n is equals to h plus 2. The reason is because so the value of h depends on like which branch we are taking here, right? So therefore, n is equals to a plus h plus 2 is not a loop invariant instruction here. All of the other instructions are loop invariant. Okay, so so the answer is, so it's not for me to comment on the difficulty of the assignment, right? And in my opinion, well, I mean, yeah, it depends on like, I mean, it depends on like how well you have learned. I mean, how well you have learned materials from the previous tutorial and this tutorial, right? Any questions before we move on? Okay, so so let's move on. So now that we have figured out the loop invariant instructions, our question is therefore be, so which instruction can we move out of the loop here? Sorry, the loop exit is the point here. So recall that so in the lecture, we said that so for an instruction to be moved, in order to satisfy the conditions for loop invariant code motion, we request that the instruction has to dominate the loop exit. So why is that the case? So let us consider let us suppose that so we have, let's say, a certain constant. Let's say c is equals to 10. And we have a for loop here. And then later on, let's say we have, let me write. And we have, let's say, D is equals to C plus 10. So apparently, the instruction D is equal to C plus 10 is loop invariant. The question is, can we which one are you referring to? Is it this one or this one?
The left one.
The what?
The left one. The one on the left.
One? This one? Oh, yes, sir. I mean, this is just the example from the assignment. Sorry. Yeah, I forgot to add the back edge here. Any other questions? Okay, so back to the example that we have here. So the question is here for whether or not we can move the instruction here to the out of the loop here. What do you think? Let's suppose that so C is equals to 10 and D is initialized to 0. Can we move the instruction here out of the loop? What do you think? Well, the answer is no. So why is it no? So let's suppose, so what happens if, let's say, we move this instruction? So apparently, at each loop iteration, D takes on the value 20, right? So why can't we simply move this instruction here out of the loop? So let us consider, so what happens if, let's say, the loop is not executed at all? It's possible, right? You can have it's valid to have a for loop that never gets executed at all. Where let's say we initialize something like I is equals to 10 and I is smaller than 0 here, let's say. Well, it's a valid for loop, but it just never gets executed. So what happens in this case? If let's say we move the instruction D is equals to C plus 10 out of this loop, what will happen is that so D will take on the value 20 here. Whereas, so the programmer, from the programmer's perspective, because this loop is never executed, so therefore he or she will be expecting that so D will take down the value 0 after this loop exit. Right? Whereas after, with our loop invariant code motion optimization, D will take on the value 20, which apparently doesn't match the programmer's expectation and hence break the program behavior. We can therefore conclude that, so in the case when an instruction does not dominate, so the reason is because so this instruction here, D is equals to C plus 1, does not dominate the loop exit. So why is that? The reason is because so if you draw the Because if you draw the CFG, you'll probably notice that. So the CFG for the for loops looks like the following, where you have the loop body here and pre-header here. And because the loop body doesn't dominate the loop exit, so therefore it is not safe to move the instruction directly to the pre-header here. And similarly, the idea holds similarly for the while loop, right? Because for loop and while loop are basically the same thing. So what about the third loop structure that we have, which is do while loop? Before we move on, is it clear to everyone why it is not safe to move instruction to the pre-header in the case when it doesn't dominate the loop exit? So what about the third loop structure that we have? If let's say now, instead of having a for loop, we instead have a do while loop. So recall this, so we have three loop structures in C or C++, namely for, while, and do while. So what about do while loop? So are we having the same problem here in the case of do while loop? Well, the answer is no. Why is that? The reason is because, as you might notice, in the case of do while loop, the loop body is guaranteed to be executed at least once, right? So that's the property of the do while loop. So therefore, in this case, it is always safe to move the instruction here to the pre-header. The reason is because in the do while loop, the loop body is guaranteed to be executed. Hence, its loop body dominates the loop exit here. So you mean the CFGs that we draw before? Is this one? Sorry, I might be wrong here because there's no loop exit here. But anyway, so the idea is clear here. I mean, for do while loop, where is the preheader? The preheader is here, right? The program point just beyond this loop structure here, right? So the question is therefore becomes, so now that we want to optimize, so is it clear? Any other questions before we move on? Is it clear why loop invariant code motion works naturally for do while loops, but not the other two loop structures, namely for loop and while loop? The reason is because, so as we discussed, in those cases, the loop body doesn't dominate the loop exit. The pre-header again is here in the case of dual. So a question therefore is, so what can we do to optimize for, let's say, instructions that doesn't dominate the loop exit? Well, there are two ways of doing it. So one way is what we call landing pad transformation. So the idea of landing pad transformation is to manipulate the CFG in such a way that so the loop body dominates the loop exit. So what does it mean here? Please note that so LVM has another landing pad instruction, and that is used for exception handling. And this is not to be messed up with that, right? So let me write the full name here. So it's called landing pad transformation. So what is the idea behind landing pad transformation? So let us suppose that we have a for loop. As we have discussed, the problem with for loop is that so the loop body doesn't dominate the loop exit, right? So it's not guaranteed that the loop body of a for loop will always be executed. The question is therefore, so now how can we make this implement a for loop using a do while loop? So the idea is that you want to transform the for loop into something like if blah, blah, blah. So this condition is exactly the same as the condition here. And then you have a do while loop. Because after this condition check, the loop body will always be guaranteed to execute at least once. And therefore, at this do while loop, it is safe to apply whatever it is that we have discussed before on loop invariant code motion optimization, right? Because in this case, the loop body here dominates the loop exit here. So therefore, it is safe to move all the loop invariant instructions here to the loop pre-header here, which is denoted as the landing pad. So yeah, before we move on, any question here on loop invariant code motion? Oh, sorry, on the landing pad transformation that we discussed. And before we, so let me erase what we have here. And the second approach, which is to optimize for those instructions, is for you to figure out in assignment 3 by using fine nodes, by leveraging fine nodes. And a hint is that So you could try to run the LLVM built-in LICM optimizer, LLVM built-in optimizer, which is LICM and plus. So in assignment 3, it comes with a benchmark that is almost the same with the control flow graph as is shown here. You can try to run this command. This passes here and see how LLVM optimizes the CFG. And this, and you'll be trying, what you'll be trying to get in assignment 3 will be exactly the same as the LLVM output here. So this is your expected output for assignment 3. Now, returning back to what we have. So yeah, sorry, we have been discussing about we have been discussing about the reason, the condition why loop body needs to dominate loop exit here. So in this case, clearly, there are two basic blocks that dominate. So if we just apply the conditions that if we strictly follow the conditions that we have mentioned during the lecture, there are two basic blocks that dominate the loop exit here, namely this basic block and this basic block. Okay, so and out of those two basic blocks, and another condition that a second, so sorry, let me just put it here. So one is body dominates exit. The second is so define once and for all. Once and for all. Meaning that so we have only one definition, and this definition will be for all the uses that we have. So clearly we have mentioned that so those two basic blocks dominate the loop exits. And because so in the loop body, we have two definitions for H here. So, and similarly for X, well, some might claim that so X, the definition for X is the same as one here. So let's just erase H here. And because so there are two definitions for Y in the loop body, so let's also erase Y here. So in the end, what we are left with is Q is equals to 7 here. So the answer therefore to the loop invariant code motion question is, so the only candidate left, if we strictly follow what we have described during the lecture, is Q equals to 7, or you might say that so X equals to 1 as well. But what happens if, let's say, we are to relieve some of the constraints that we have discussed during the lecture? What about all the other loop invariant instructions? So let's just place them back. Let's say we are optimizing at the LLVM IR level, which adopts the SSA format, and hence there is no issue for a single definition, because those like those definitions will be mapped to different variables or different values. So what will happen in those cases? What will happen if, let's say, we are to relieve those two constraints? Again, so check how our VM optimizes the CFT. And it will be your expected output for assignment 3. So what we'll be seeing in assignment 3 is how our VM optimizes. So I remove the ambiguity here, because as we mentioned, so s equals to 1 is I removed s equals to 1 in the benchmark for assignment 3. And in assignment 3, you will see how our VM optimizes the code that we have here by removing all the loop invariant instructions. How it optimizes this graph by moving all the loop invariant instructions to the pre-header here. Well, move some of the loop invariant instructions here to the loop exit. Check this out. I keep this down. Any questions here? Yeah, and I think the final question, I think that needs clarification is that so we have mentioned that for some instruction, we should move it to the pre-header. Well, for some instructions, we sync it to the loop exit. So consider, for instance, the loop invariant instruction that we mentioned previously. Let us consider Q is equals to 7 here. Or let's consider a more simple scenario where we have, let's say, this do again. So we have this do while loop. Let's say we have D is equals to C plus 10. That is loop invariant. So now that we have mentioned, it is possible to move D is equals to C plus 10 to the pre-header. So what about we sync it to the loop exit here? So let me mark this as solution 1 and the other is solution 2. So which one do you think is a better solution in this case in terms of loop invariant code motion optimization? Or which one do you think is a better solution here? Anyone? Assuming that so the only use for D is outside of this loop. Why is it 1? Assume that so we move the instruction here to here. So let us consider again from the register usage perspective, right? So if let's say we move the instruction to here, what happens is that so we will need a register value to hold the value for D, and this register will always be live while this loop has been iterating, right? But however, if let's say we are not using this value D, then there's no reason why we should have a register that hold the value of D while this loop has been iterating. So on the other hand, if we sync it to the loop exit here, what happens in this case is that at this loop iteration, we'll have an extra free variable for handling all the variables within this loop, right? And after this loop exit, we have another register to hold the value of D. So the answer is solution 2 is better in this case. The reason is the idea is similar to what we have discussed in lazy code motion because it has less register usage here. Yes, that's right, exactly. So as you can see how as you try to experiment with the LVM building optimizer, you will see how it syncs those two instructions at the loop exit, while moves all the other loop invariant instructions to the pre-header. Because it tries to sync instructions to the loop exit whenever possible. Okay, and for the other instructions, because they cannot be synced to the loop exit, so therefore they are moved to the pre-header. Any other questions? Again, so if you have any questions, please make sure to always ask now, because you annually need to deal with it as part of your assignment. Any other questions about either lazy code motion or register allocator, well, anything related to what we have discussed today or assignment 3? Again, so I will update I will update the website after this tutorial. Questions, concerns? So in the assignment 3, you will be optimizing this loop, this benchmark, with loop invariant code motion optimization, and then so the output of your optimizer, as always, is the IR, right? And in addition to optimize this CFG using loop invariant code motion, you'll be trying to map the optimized IR to actual machine assembly code that can be executed on real hardware. Okay, and the way you're going to do that is that you're going to implement the interference graph register allocator as we have discussed during the lecture. Okay, so this is the programming portion for assignment 3. Questions, concerns? We still have 1 minute. Okay, so if no, that's all I have for today. Thanks, everyone.